You know, when you buy an electric vehicle, uh, the expectation is usually that the absolute hardest part of the whole transition is just getting used to the car itself.
Right, yeah, like figuring out how the dashboard works or, dealing with the new app.
Exactly. You figure, okay, I've got the car. I know how the screen works. Now I just need to plug it in. But then you start looking at the public infrastructure and you realize that the plug isn't actually the problem.
No, not at all.
The charger itself isn't really the bottleneck.
Hmm.
According to this really fascinating profile we're reading in Awards Insider today, the real obstacle, like the massive invisible wall sitting right in front of the entire EV transition, is actually the electrical grid itself.
Yeah, it really is the ultimate hidden constraint. I mean, we've spent the last decade innovating so rapidly on the vehicle side, right? Putting in better batteries, extending the range, engineering these ultra-fast charging capabilities inside the cars.
Right.
But we have essentially outpaced the physical wires that deliver the power to the stations.
Which is just such a wild concept to me. Like, we built the supercars, but we completely forgot to pave the roads.
Yeah, that's exactly what it is.
And that is exactly what we are getting into today. Welcome to today's deep dive. We are looking at a specific piece of technology that approaches this whole issue not by trying to, magically rebuild the entire grid overnight, but by kind of tricking the grid into working for us. So our focus today is XCharge North America's GridLink. This system just won the 2026 E&E Leader Judges Choice Award for Business and Infrastructure.
Which is a huge deal in that space.
Oh, absolutely. And we're using their official product specifications along with that award profile to figure out how they are actually pulling this off.
Well, the documentation gives us a really clear window into the economics of energy, honestly, because this system approaches an infrastructure problem not as some massive civil engineering project, which, it takes decades, but as a localized product design challenge.
Okay, let's unpack this, because before we can really appreciate how this machine works, we have to establish why EV chargers are so incredibly difficult to deploy in the first place.
Right, the baseline problem.
Exactly. Because for you, listening right now, if you've ever driven through a rural town or, say, an older commercial district, and you wondered why there isn't a fast charger at the local grocery store, it's not for a lack of wanting one. It's basically an issue of physics.
Yeah, the grid just isn't there.
Right. Think about traditional DC fast charging, like trying to fill a massive fire truck using a standard residential garden tap.
Yeah.
The demand for the water, or in this case the electricity, is simply too high, and the pipe delivering it from the street is just way too small.
I love that. That garden hose analogy perfectly illustrates the structural deficit we are facing here. To install a traditional DC fast charger, a site needs a massive high-voltage utility connection.
Right.
And a standard commercial building simply isn't wired to handle the sudden, massive draw of power required to charge an EV in 20 minutes.
It'd just blow the system.
Exactly. In many locations, particularly those outside of, newly developed, highly dense urban centers, that level of grid capacity simply does not exist on the local utility pole.
Okay, so let's make this concrete. Let's say I own a diner off Interstate 80. I see all these EVs driving past, right? And I want to capture that business. I have the money. I want to buy a fast charger, and I just want to put it in my parking lot. What actually happens when I call the utility company?
Oh, you trigger a cascading series of physical and bureaucratic hurdles.
Uh-oh.
Yeah. First, the utility assesses your local grid, and they tell you that the local substation or the transformers on your street cannot handle the load.
Okay.
So you have to pay for costly utility upgrades. You literally have to foot the bill to have the grid infrastructure expanded all the way to your site, which involves trenching new high-voltage lines.
Wait, me, the diner owner? That sounds incredibly expensive.
It is. It's often prohibitively expensive. But the crazy part is the cost isn't even the biggest barrier. It's the time.
Oh, right, the bureaucracy.
Exactly. You enter what's called an interconnection queue. You are just waiting for the utility to engineer, approve, procure parts for, and then finally process your connection.
Wow.
The documentation notes that these queues routinely stretch from months into years, and that is all layered on top of complex local permitting processes for actually digging up the pavement.
So a business could have the capital, have the desire, physically buy the charger, and then just sit there looking at an uninstalled piece of metal for 3 years while they wait for the local utility to catch up.
Yeah, that is the unfortunate reality for thousands of businesses right now. And the implication of this is profound on a macro level.
How so?
Well, it creates what the industry calls charging deserts. Because the infrastructure upgrades are so financially or practically unviable, Entire geographic areas are just completely cut off from the EV transition.
Oh, wow.
Yeah, we're talking about rural corridors, older commercial districts, and historically underserved communities.
Yeah. So they're essentially penalized for having older grid infrastructure. The transition just clusters where the grid is already strong and wealthy and leaves massive geographic gaps everywhere else.
It creates a tremendous bottleneck. And for the site hosts who do actually try to build in these areas, they face not just those upfront capital costs, but tremendous operational risks tied to energy pricing.
Right.
Once that charger is finally running, drawing massive amounts of power from the grid during peak hours can, financially ruin a small business.
Which brings us to the actual innovation we are looking at today. Because if we accept that waiting for $1 trillion grid overhaul is kind of a fool's errand, the only logical place left to innovate is at the very end of the wire.
Exactly.
So what does a machine look like that can trick a weak grid into delivering a massive charge?
Well, you have to change the fundamental architecture of the charger itself. You have to totally decouple the act of pulling power from the grid from the act of pushing power into the car.
And this is the part I was reading in the specs where I really had to stop and push back on the physics. Because the specs claim this single machine, this GridLink system, can just plug into a standard connection and somehow deliver 300 kilowatts of power to a car. But wait, if the grid can't handle a massive power draw, how is that physically possible? Furthermore, moving power from the grid into a stationary battery and then later into a car battery, doesn't that inherently result in some energy loss? Are we just wasting power to save time?
That's a great point. But what's fascinating here is how the system leverages time to basically negate those exact concerns.
Okay, tell me more.
Yes, there is always a marginal efficiency loss when transferring energy between batteries. That's just physics.
Right.
But the core innovation of GridLink, which is heavy battery integration, accepts that tiny physical loss to gain a massive infrastructural and economic advantage. It places a huge buffer between the fragile grid and the demanding vehicle.
Ah, the battery buffered bypass.
Exactly. Think of it as a sip versus gulp mechanic. Instead of pulling a massive instantaneous gulp of power directly from the grid the moment a car plugs in, which is what causes all those infrastructure headaches and requires those expensive high-voltage lines, GridLink slowly sips power from the grid over a long period.
Oh, I see.
Yeah. It does this during off-peak periods, usually in the middle of the night, when electricity is incredibly cheap and grid demand is at its absolute lowest. It stores that energy in an integrated 215 kilowatt-hour battery.
And the specs note that the battery is modular, right? You can actually upgrade it to 430 kilowatt hours if your specific location has higher traffic and you need to double the capacity.
Exactly. So the system just sits there, quietly accumulating energy without stressing the local grid connection at all. Then when an EV pulls up at noon and plugs in, the GridLink system doesn't ask the grid for anything.
Wow.
It just delivers that stored energy directly to the vehicle at high speeds, up to 300 kilowatts of DC fast charging.
So going back to the fire truck analogy, it's literally like filling a massive water tower with a garden hose overnight.
Yes, perfect.
The garden hose doesn't break, the local water pressure doesn't drop, but when the fire truck arrives, you could just open the floodgates of the water tower and fill the truck instantly.
It completely insulates the grid from the shock of the charging event.
That's brilliant. But the physical specs on this thing are what really stand out for someone actually trying to run a business. Because when you hear 215 kilowatt hour battery and 300 kilowatt outlet, the average person probably pictures like a giant shipping container.
Yeah, you'd think it would be massive.
Right. But it's designed to be incredibly flexible. It features dual input compatibility, meaning it can take both 208-volt and 480-volt connections without any hardware modifications required.
And that dual input design is totally crucial for deployment speed. It means our hypothetical diner owner doesn't have to rewire their entire property to match a specific charger requirement. The machine just adapts to the power environment that is already there.
Because if you own a small commercial lot, you don't really care about the internal wiring, you care about the footprint and the installation pane.
Right, absolutely.
The hardware uses in-house developed, liquid-cooled 60 kilowatt power modules.
Yeah.
You can literally plug this system into a standard 60 kilowatt industrial socket.
Which is wild.
Right. For context, for those listening, a 50 kilowatt socket is the kind of connection that runs a large commercial oven or heavy factory machinery. It is not a specialized, multi-million-dollar high-voltage substation line.
Not at all.
And all of this The batteries, the liquid cooling, the dual ports with extendable cable management, the 55-inch touchscreen, it all fits into a sleek, thin-walled footprint of less than 24 square feet.
It is essentially the size of a standard commercial washer and dryer set.
Less than 24 square feet. You can fit that across a single parking space width.
Yeah.
That fundamentally changes the math for a site host. You aren't giving up a massive chunk of your commercial real estate to house the infrastructure, and you aren't losing valuable customer parking.
And you aren't digging up your parking lot for a year to lay new conduit.
Exactly.
The installation timeline collapses from years down to weeks. The friction of deployment is almost entirely removed.
Here's where it gets really interesting, though. Because everything we've talked about so far is just about solving the location problem. How do we get a fast charger where the grid is weak?
Right.
But GridLink software fundamentally changes its relationship with the broader electrical grid. Because historically, EV chargers are basically just energy vampires.
Yeah, they just sit there and drain power from the system.
Exactly. But this system actually gives back. Explain the mechanism behind how a charger becomes a grid asset.
Okay, so it comes down to transforming the charger into a distributed energy resource, or a DER. Because GridLink has that massive internal battery, and because it is equipped with bidirectional capabilities, specifically battery-to-grid or B2G technology, it isn't just a one-way street taking power from the utility.
It's an active participant on the network.
Yes. During a demand response event, when the regional grid is under severe stress, say during a massive heat wave when everyone's air conditioning is running and the utility is begging people to use less power, GridLink can actually reverse the flow. Yeah, the utility can signal the charger, and the charger can push its stored energy back onto the local grid to help stabilize the system and prevent brownouts.
And it also allows for direct integration with solar power systems, right? The specs say it can handle up to 60 kilowatts of photovoltaic input. Now, I have to push back here a bit.
Okay.
60 kilowatts of solar input. Isn't that just a drop in the bucket compared to a machine designed to output 300 kilowatts to a car?
Yeah.
Like, does the solar actually move the needle?
It absolutely moves the needle when you consider the time-shifting element. You see, you aren't trying to charge the car directly from the sun in real time.
Okay.
You are using that 60 kilowatts of solar to constantly trickle charge that massive 215 kilowatt-hour battery all day long. You could have a solar canopy over the parking lot feeding directly into the charger's battery, completely bypassing the grid entirely for a significant portion of its stored energy.
It creates a localized micro-ecosystem of energy generation, storage, and dispensing. And to manage all this, the system relies on dynamic power allocation and what they call smart energy management modes.
Yeah.
Because the operator obviously needs to be able to tell this machine how to behave based on their specific business needs.
Right, you need that control.
So there are 4 main modes. Let's break those down. First is max mode. This is pretty straightforward. It pulls maximum power from both the grid and the internal battery simultaneously to deliver the fastest possible charge. You'd use this in high-demand scenarios, maybe a busy highway rest stop, where minimizing customer downtime is literally the only thing that matters.
Yeah, that makes sense. Then you have eco mode, which kind of flips the priority. It optimizes for cost and efficiency by prioritizing the internal battery and any attached renewable sources, like that solar canopy we mentioned.
Right.
It deliberately reduces reliance on the grid. And we really need to explain why this is so critical for businesses. Peak demand charges.
Yes.
Right.
Explain how punishing those fees actually are, because I think most residential listeners have no idea how commercial electricity is billed.
It's brutal. Utilities penalize commercial sites for sudden spikes in usage. You don't just pay for the total volume of electricity you use in a month. You pay a massive fee based on your highest 15-minute spike in demand.
Just a single 15-minute spike.
A single 15-minute spike from a traditional fast charger pulling power directly from the grid could cost a business owner more than their entire monthly lighting bill.
That's insane.
So eco mode ensures you are dispensing the cheap power you stored overnight, physically preventing that spike, rather than pulling expensive, penalized power currently flowing through the grid.
It essentially protects the business from accidental financial ruin.
Hmm.
Okay, so then there's custom mode, which lets the operator tailor the output to their specific site limits or local pricing structures. But the fourth one is the one I really want to zero in on, reserve mode. This feels like a massive leap forward for infrastructure resilience.
It really is. Reserve mode ensures that a designated portion of that energy storage system is always held back, always isolated, and available just for emergencies.
So, if there is a severe blackout, The grid goes completely dark due to a storm or whatever. This charger doesn't just become a useless piece of metal blocking a parking space.
No, it keeps running.
It can keep charging cars so people can evacuate, or because of its bidirectional nature, it can be routed to ensure critical building systems like the refrigerators in a grocery store or the lights in an emergency shelter keep running.
Exactly.
But the part that really caught my eye in the specs is the financial side of holding this reserve. It allows site hosts to actually utilize that energy for ancillary grid services.
And this changes the entire economic model of EV infrastructure. The site host isn't just saving money by avoiding peak charges, they are potentially earning active revenue.
Wow.
Yeah, by offering that reserved capacity back to the utility to help balance localized grid frequencies, the EV charger transforms from a sunk capital cost into a revenue-generating grid asset.
So the utility actually pays the site host for the privilege of accessing that battery buffer?
Yes, exactly.
So what does this all mean? I mean, theoretical technology is great, a smart spec sheet with 4 cool modes is great, but in the sustainability and infrastructure space, awards are won through actual verifiable deployment.
Always.
Which brings us back to the 2026 E&E Leader Judges' Choice Award for Business and Infrastructure. Why did this specific product rise above all the other concepts to win the judges' choice?
It really comes down to hard, verified numbers. The judges in these sustainability competitions, they see endless projections, 3D renderings, and tiny pilot programs that never actually scale.
Right, a lot of vaporware.
Exactly. But according to the award's insider profile, GridLink is well past the pilot phase. It is actively deployed at over 50 sites across the U.S. and Canada.
Real-world proof, actually sitting in parking lots today.
And the operational data from those 50 sites in 2024 is what sealed the award. In that year alone, these deployed systems delivered over 1.1 gigawatt hours of energy to vehicles.
Wow, 1.1 gigawatt hours.
Right.
That is a massive amount of electricity flowing into vehicles in places that previously might not have been able to support a charger at all because they were stuck in those interconnection queues.
Exactly. But the environmental metric is even more important.
Okay.
By operating the way it does, charging its battery overnight and dispensing during the day, it actively avoids drawing carbon-intensive peak power. The award's insider profile states that GridLink systems avoided 2.91 million pounds of CO2 emissions in 2024.
Okay, let's explain the how behind that statistic, because a lot of people assume electricity is just electricity.
Right.
How does changing the time of day you pull power from the grid actually reduce CO2 emissions?
It has everything to do with how utilities manage supply and demand. The baseload of the electrical grid, like the power humming along at 3:00 a.m., is often supplied by consistent, cleaner sources like nuclear, hydroelectric, or wind power. But when the grid peaks at 5:00 p.m. and demand skyrockets, utilities are forced to fire up what are called peaker plants. These are almost always older, highly inefficient, and very dirty natural gas or coal facilities. So because GridLink charges its internal battery at 3:00 a.m. using that clean baseline power, it physically prevents those dirty peaker plants from having to turn on at 5:00 p.m. to charge a car.
It's not just making charging accessible, it is literally making the energy dispensed demonstrably cleaner by timing the energy market.
Yeah, and if we connect this to the bigger picture, the value proposition here operates on multiple levels simultaneously. For the site host, by avoiding those peak demand charges we discussed earlier, they are lowering their operational costs by up to 30% compared to a traditional charger.
Which means the business case for our rural diner owner actually pencils out. They can make a profit selling electricity.
Exactly. And for the grid operator, the utility company, this system reduces the required grid capacity for a fast charging station by an estimated 50 to 80% compared to conventional DC fast chargers.
A 50 to 80% reduction in required grid capacity. That is literally the difference between a utility looking at a permit and saying, yes, your current street pole can handle this, approved today, versus saying, well, we'll need 3 years and a massive substation upgrade to handle your request.
Right. It entirely removes the friction from both sides of the equation. And that's exactly why it won the award. The award's insider profile actually included a quote from one of the judges that perfectly summarizes its impact.
What did they say?
The judge noted that the most valuable thing GridLink does isn't just optimizing charging where infrastructure already exists. The true value is making high-speed charging possible where it previously wasn't.
Fast charging where the grid said no.
Yes.
Whether you're looking at a remote gas station, a national park, an older commercial center, or some sprawling industrial facility, It completely rewrites the map of where EV infrastructure can go.
And this raises a really important question about how we view constraints as a society. We have an aging, fragile grid. We have surging power demands from EVs, data centers, electrification. Rather than waiting for a multi-trillion-dollar national grid overhaul that may take 30 years, this technology adapts to the bottleneck right now.
Which is such an empowering takeaway for you listening right now. Whether you manage a commercial property, drive an EV, and worry about range anxiety out in rural corridors, or just care deeply about the logistics of the energy transition,
Definitely.
understanding that infrastructure can be smart enough to adapt to physical constraints, rather than just waiting helplessly for the grid to eventually catch up, is a completely game-changing perspective.
It proves that the bottleneck doesn't have to be a blockade. Innovation can happen at the very edge of the network, smoothing out the massive imperfections of the legacy utility systems we are forced to rely on.
And that leads me to a final thought I want to leave you with today. Just something to mull over as you look at the changing landscape of our cities and highways.
Let's hear it.
If everyday locations, like local gas stations, national parks, neighborhood grocery stores, roadside hotels, all begin adopting these battery-integrated bidirectional systems just to solve their own local charging problems, what happens when thousands of these units are out there, networked together?
That is the ultimate frontier of distributed energy.
Are we quietly, almost accidentally, building the world's largest decentralized bidirectional battery, cleverly disguised as a network of EV chargers?
When you look at the trajectory of the hardware, it certainly looks that way.
If you have questions about being a part of future segments or other partnership opportunities, reach out to a member of our team today. Links are located in the body of this session's description.